defense from the Nayak and supervisor Dr. co-supervisor Dr. Lee, and the committee member W and Dr. Nayak. And today you'll give a 30-35 minutes presentation, and then we'll have questions from the audience. And then after that, we may ask audience to leave, but depends on the day. And then we'll have a question from committee member. All right. And now the floor is yours.
Thank you, Dr. Rupai, for the introduction. My name is Dev, and welcome to my defense. Our work focuses on the computational investigations on hydrodynamic performance of active and passive pitching of the Carangiform swimmers. So, sorry. So this pointers.
Click on the slide because you are on Zoom, so now it should work.
Okay. Yes. So sorry about that. Through nature, all the swimmers, they have their distinct way of using their body for propulsion in the underwater. We look at shark. Shark have a very different caudal fin compared to, let's say, eel. Now, when we compare eel to either tuna or trout, we see a variety and variation in their caudal fin. Now, it's not just the way it exists. There are very specific reasons behind that. When we look at shark, it's an asymmetric caudal fin. The upper lobe focuses on the much more elongation, whereas the one on the bottom is not as prominent. That's because they don't have the swim bladders. So they not only focus on propulsion, they also need to produce lift. Whereas now on the other side of the spectrum, we see eels. They have somewhat like a flappy caudal fin, so they don't use their caudal fin for propulsion primarily. So their motion as well, we can look at here, they use the entire body for maneuverability. Now, when you compare a tuna or a trout, they belong pretty much to a same group, which is Carangiform swimming mode. They use majorly their rear end of the body to produce propulsion. And for example, we can look at the tuna, which has much more prominent and sharper looking caudal fin, and they are also one of the fastest swimmers. So now this, alongside the other literature review that we did, creates the key framework questions, which are the purpose of the study, what is the novelty, how did I conduct the study, what does the study reveal, what is the significance, and further end, what future does this study holds. Now, from the literature, we picked jackfish model for our study, and here we can see that the caudal fin produces somewhat like an undulatory motion. This motion has been researched, and it produces these vertical structures. Based on the study in 1995, it is used for creating propulsion. These vortices basically carry the energy and transfers the energy through the water, and that propels the body in underwater. And not only just the fish, it's more of like a reflection on the evolution of these swimmers. Here we can look at a dead trout, which was placed using a string in the wake of a bluff body, and they use the energy from the vortices to create propulsion. Another study shows the interaction between the dorsal fin and the caudal fin to create propulsion, and the vortex dynamics between them through experimental work. Moving further, there's been a lot of studies, including 2D and three-dimensional analysis that focuses on the same aspect. Here we have one of the study that focuses on understanding two airfoils in tandem arrangement in two-dimensional study that focuses on how they can use a completely different Gaussian envelope, and they were able to generate 90% efficiency. Another study here shows how these vortices are contributing towards thrust, and we'll dive further into it as we progress in these slides. Recently, we have come across a lot of studies which focuses on the function of the caudal fin. Here we can see the study by CO et al. Have focused on the scaling laws of their vortex dynamics and the swimmers. Now, when we look at the caudal fin of this swimmer, the research by Kumar et al., they modeled the caudal fin with completely flexible body, which mimics a very similar kinematics to the swimmers itself. And even in the past, we have seen they have built robots based on the analysis and the study that they have performed through bluegill fish. And recently another research that came out which focuses on using a nonlinear stiffness for creating larger amplitude for propulsion. But here they have used fully passive joint. Moving further, we must establish how we use the terminology to describe these different kinematics in the motion. For the fully active model, we have the active heaving and pitching as an actively controlled, which is where we define the motion. It's not dependent on the flow itself. It's going to be something that we will derive. Semi-active is the mix of both. We control half of the flapping through external forces, let's say use an actuator, and we just use a spring or a damper to just let it freely move on the other axis. Whereas when we compare the fully passive motion, we just use torsional spring or linear spring and dampers and just put them in the flow domain and let it move based on the vortices itself. This leads to the main hypothesis of this research. The first one was the caudal fin would primarily contribute towards the production of thrust in the swimmers. Then the passive pitching of the caudal fin should contribute and help improve the performance of this Carangiform swimming mode. And the last one would be the nonlinear stiffness and how that affects the pitching kinematics of the Carangiform swimmer. And this part of the analysis was done in 3-dimensional study. Now, that also created a basis for our research objectives. We got 3 objectives that focuses on the 2-dimensional study. One, we use the active pitching, where the entire kinematics of the swimmer is controlled by us. The second one, we leave the tail to pitch freely using spring and a damper. And the third one is to compare the kinematics. Is a passive pitching tail better than an active one? The third one is going to be very similar to the 2-dimensional analysis, but the difference is that we use the nonlinear stiffness to amplify the pitching motion. So here again, we will evaluate the performance of the swimmer in 3D with active pitching. We'll do the same for passive pitching, and then we'll compare the kinematics. So further, now the way we have designed the model of the joint is for the 2-dimensional study, reading the dorsal view of the swimmer, and we use 2 airfoils to mimic the geometry. But in the 3D, we have used and modified the actual model of a jackfish. And what we have done is we have placed at the peduncle is where we have placed the torsional spring and the damper to create this passive joint for the pitching. And we have the normalized component of the stiffness, viscous damper, and the inertia. Now, when we look at the dynamic model in 3D, the spring is placed in a way that the caudal fin can pitch freely about its y-axis, or we can see from the dorsal view that it just moves from the top. And there is other pitching axis, we are just constraining that out of the equation. This is the governing force balance equation that shows and governs the pitching of the swimmer. So what we have done is we've used the damper, we have also used the stiffness, and that is equal to the moment coefficient that we have for the swimming mode. Now here in this equation, we can segregate this equation into 2 components, one for the linear model and the other for the nonlinear. So for the linear model, we have just used the pitching angle in the equation, but for the nonlinear stiffness, we incorporated a forcing term and a stabilizing term. So one force basically will make sure the pitch of the caudal fin goes to a larger amplitude, whereas the other one, the cubic nonlinearity, kicks in and it will stabilize the system when it reaches diverging oscillations. Now that explains the passive part of our system. Moving on to the active part, which is the undulation, heaving, and pitching. We use the Carangiform swimming equation to model the kinematics of undulation. Heaving is controlled by a very similar equation, but we only use that for the caudal fin, and the entire caudal fin will heave as altogether. And we use a derived pitching equation, And it's designed in a way to make sure when it's combined with the heaving, it will follow the similar kinematics of an undulatory body. So the amplitude that the tail's trailing edge would trace will be very close to what we observe in undulatory swimmer. One common aspect that we see here is the function that we see in all three equations. That played a very important role in all of our simulations. So we modified the original equation using a sigmoid function. What that does is it will incorporate a smooth start to make sure that the system starts from a very converging point and then it reaches steady state faster. Usually, I observe that my simulations tend to achieve steady state within 5 to 6 oscillation cycles. Whereas before it was saying almost close to 30 to 35. That also saved a lot of our computational time. Our numerical methodology is we have used the finite volume method using the OpenFOAM platform, and we have just directly solved the Navier-Stokes equation, and there was no turbulence modeling incorporated here. And these are the continuity equation and the Navier-Stokes equation. We do not have any external forces, so we only account for the viscous and the pressure term here. The grid is very important because it ensures that all of our result is valid. In my seminar, I did show the grid convergence and time step independence study, which is why it's not here. But this is the grid that was used and is used for the current study in the two-dimensional analysis. The geometry of the swimmer is designed using NACA 0015 as the body and NACA 0012 as the tail, which is caudal fin in the case of the 3D study. We chose a medium grid, which gave us promising results. And again, that was part of my seminar, which is why now we can move to the three-dimensional grid. So here we got the moving mesh. We use a very similar approach for the moving mesh in 3D as what we did for 2D. It's the quadratic diffusivity. When we look at the grid topology, we have made sure the grid cells and the convergence gives us very accurate results. So we went with 50% increment for each grid. So from coarse grid to medium grid, we have 52% refinement. From medium to fine, we have 48% refinement. That yielded 40 million, 29 million, and 56 million grid cells. Moving further, here we have shown the grid independent study. So if you look at the dorsal view and the vortices from that, we can see that the coarse, medium, and fine grid shows a very close resemblance alongside the CD and CL one. So to save computational resources and time, we chose the coarse grid, which gave us reliable results as the final grid size for our cases, which was 14 million. The validation was an important part. For a two-dimensional study, we only used one of the simulation case from the research. But for 3D, we ran 3 simulations and validated all the results through the study from Cullen et al. Here, we use a very similar geometry. We see the variation in the results that primarily comes from a few factors. First is that we have not accounted for the dorsal fin and the anal fin. And secondarily, we have used a little bit of a different aspect ratio because we wanted to make sure that the overall length of the swimmer stays exactly the same. So we had to shrink the trunk and the caudal fin, which shows the variation. What we did, we were able to capture the key findings from the research, which was in the 2 oscillations at lower wavelength, they reported the peak occurred in the first half of the full oscillation, whereas in the second 2 half, when the wavelength was more than 1, they got the peak in the second half of their oscillation cycle. So that created a very strong basis for us to claim that our methodology was valid. Now for the design parameters, we have shrunk the spectrum for choosing the variation in parameters a little bit compared to the two-dimensional study. Here, we use the damping ratio from 0.3 to 0.45 with the increment of 0.05. And we have choose this tuning parameter, which we will see further in, that make sure that our pitching is in phase with the heaving of the caudal fin. And the Strouhal frequency and Reynolds number is calculated based on its viscosity, free stream velocity, and the David amplitude, and the length of the swimmer. So now we can look at the first aspect, which is the two-dimensional study. In the 2D study, we see the actively pitching tail, which is also have been reported in a lot of research as well, which shows that with increasing the Reynolds number and the tail beat frequency, we do see larger thrust production, and that can be seen from this plot here as well. Now, when we compare this with what we observe in passively pitching tails, here we see a much more scattered plot here, firstly, at Reynolds number 5000, but when we look at Reynolds number 500, we see a trend, which is with increasing the Strouhal frequency, and if you look closely, with increasing the damping ratio and the moment of inertia, we do tend to move towards the thrust dominant region. Now, not only the thrust is important, but for the two-dimensional analysis, we have incorporated a power ratio that shows how actually our swimmers perform. Here, we can see the dark line shows the trend of the actively pitching tail, and anything that falls above this trend shows the better performance in terms of their swimming capabilities. Another aspect we can grasp from this is that for Reynolds number 500, there are a lot of other cases that can produce better performance compared to Reynolds number 5000. And now we can understand why that would happen from the perspective of vortex dynamics. So when we look at the actively pitching tail, because it follows a very close trajectory, that of an undulatory swimmer, we can see that the vortex slides down just through the body and then sheds in the wake. When we capture this instant, let's say we capture the 3 vortices right when it sheds, we can name them V1, V2, and V3 based on their sign. So the positive vortex would be rotating anti-clockwise, and the negative vortex rotates clockwise. And what that do? So whenever the vortex would rotate, these 2 vortex would contribute towards a net dipole velocity. So it would create somewhat like a velocity component between those 2 vortex structures. Similar effect will be observed between these 2 another vortex. So what that does? So now these components would have one lateral velocity component in the spanwise direction and one towards the streamwise direction. Now we can look at the streamwise velocity. That's the one that contributes towards the production of thrust. So this majorly, when we look closely in the wake, that comes from the pressure thrust, basically, because it's in the wake. And if the U stream is greater or larger than the free stream velocity, that's considered better because that shows much more speed, higher speed of the swimmer. Now, we can look at the wake. Here we can say the 8 vortices. We plotted that using the Q criteria 300. From here, we can see each of these vortex would contribute towards net streamwise velocity. All that actually helps a lot because that shows that we were able to go up to speed 6 times better than the actual swimmer, than this free stream velocity. On the contrary, we can see the passively pitching tail. It looks very similar, but there are a few differences. And the major one is that we see the vortex from the leading edge just gets detached primarily because the tail is not able to increase the angle of attack because the pitching is not that high. The amplitude of pitching is very low, which is why we see, because of this detachment, there's a lot of incorporation from viscous drag. Now, we plotted the maximum velocity region. Although we see these vortex structures and the wake that contributes and shows towards higher velocity, we can look closely by plotting the minimum average velocity over one oscillation cycle. That's from the -1 to 0, and see that it's predominantly here around the airfoil, and that's the reason we see much more higher thrust in the actively pitching tail compared to its passive counterpart. Now, we need to draw a correlation and a basis for investigation, for the investigations in 3-dimensional study. The first is the passively pitching tail do not achieve large amplitudes. Now, can we do that by using a nonlinear stiffness in 3D? The second one is that although the passively pitching tail shows a larger power ratio, we do not see a larger thrust. Can we do that if our amplitude is at higher value, if we can achieve the amplitude of pitching compared very similar to the active case? And the last one is we only were able to see the production of thrust at higher frequency. Can we do that at lower Strouhal frequency? because in actual fish, they do tend to swim with through-hull frequency of 0.3 and a Reynolds number 3000. So they do produce thrust. Now, if we just go by the analysis from our 2D study, that doesn't seem possible because we did not see a large reduction of thrust. Now, for that, what we did is we ran a variety of simulations with the variation in the controlling parameter n and the damping ratio zeta, from which we move forward with the investigation in the study where the fundamental frequency comes very close to the heaving frequency, which is 1.75 hertz. And that comes from this true hull frequency of 0.3. And because this configuration in the diagonal showed us prominent results, we further increased the range at which we ran the simulations to the zeta 0.450 and n equals to 60. Now, the convergence criteria, we need to make sure the nonlinearity of the system stabilizes before we make any claims or further study anything. Here, what we did is we plotted the frequency of each oscillation after the completion of one cycle. So within 7 cycles, most of the cases with higher zeta tend to converge and do not change their frequency. So what we did is we used an error equation. Here we can see if the variation or the change in the frequency is less than 1%, we can call it stable in terms of its pitching amplitude and frequency. And we skim through those parameters and now we further investigate these cases to see what part of this contributes towards thrust and the performance matrix. Now here we can see the stable pitching displacement. All the cases we had, we plotted their displacement and we distinguished them using this term we have used. It's PLS, which is phase lag synchronization. So the reference case is the active pitching. So the displacement of the active pitching, if there is a lag in terms of it's behind the displacement of this passive control, that's going to be incorporated as PLS, which is phase lag synchronization. If it's advancing, so it's going to be phase advanced synchronization. So that shows that the pitching is leading the motion compared to its heaving instead of being in actual phase. Now, we can look at the case with, let's say, maximum distortion, as in higher phase angle between them, and the one that shows a very close resemblance to the pitching kinematics of the actively pitching tail. Now, based on our study, what we found is the best performance was actually coming from the case that shows a close resemblance to the actively pitching tail, compared to the one that shows the one with the maximum lag. Now, to solidify our claim, we can further investigate this in terms of their vortex dynamics and their actual amplitude displacement. Here, what we'll consider is the Carangiform swimmer, their trailing edge would follow a trajectory and a lateral displacement. What we refer to that as the tail beat amplitude. Now, this tail beat amplitude creates the basis for our analysis. The actively pitching tail is designed and modeled in a way that it follows a very close kinematics to the Carangiform swimmer itself, and it shows that it does not really leave the range of the tail beat amplitude for the Carangiform swimmer. When we look at the best performance case, which is at lower zeta, here we see that the tail beat amplitude follows a very exact similar resemblance to the actively pitching tail. Now, when we move on to the case that shows inferior performance, the phase advance actually goes a very large amplitude. Now, that does create larger vortex activities in the wake, but that does not necessarily contribute towards thrust, and we'll see that further. Now, when we look at the swimmer and we take the dorsal view, we can look at their vortices in the wake. Here I've used the term wake spread angle, which apparently shows how further away in lateral direction does the wake spreads in terms of the vortices. For the case that shows the better performance, it's very narrow, even narrower than the actively pitching tail. But in terms of the case that shows inferior performance, it spreads largely, almost 2 times that of the actively pitching tail, which might be better because it shows much more vortex activities, but does not actually contribute towards thrust. We have observed similar finding from one of the study in 2018. So what they show is, here in case 1, there is much more activities happening in the streamwise direction, but alongside that, we also see a a lot of the velocity in the lateral direction. Now in case 4 here, we can see that the activity is happening in streamwise direction for the velocity is very low, but there is almost no lateral distortion. So based on their analysis, this case 4 showed better performance. So that's the observation we have made in our cases as well. Now when we plot their CD, we can see that for the passive loop pitching tail, it shows very close resemblance to a neutral value, which is not very dominant in thrust or drag, which is close to what we see in the active loop pitching tail as well. Or for the passive loop pitching tail with a better performance shows a much more time span in the thrust direction, which is in the bottom half. So the negative drag is what we consider thrust. Now we can look at the vortex dynamics aspect of this and why does that happen. So when we look at the vortices in an isometric view, we can see that in every half oscillation cycle, there is one ring vortex that is being shedded. Now this ring vortex, when we look further and investigate what happens, is this vortex basically rotates inwards. So when it actually rotates inwards, that creates somewhat like a jet, it creates a jet-like effect that contributes towards thrust. And we can observe that by plotting the velocity diagram, instantaneous velocity diagram when this vortex is shedded. So we can take the sectional view from 0, 0.2, and 0.4 in the z direction. And when we look closely, around the trajectory, when we see the frame of the vortex, it creates a very narrow jet-like effect around that ring. That is the one that contributes towards thrust. This is very similar finding that was reported by Don et al. In Fluid Mechanics Journal in 2006. What they observed is all these ring vortices, they create a jet-like effect, and one of those components would contribute towards thrust that's in facing the streamwise direction. And the other component would go towards the lateral direction. Now when we compare the vortex dynamics and the dorsal view of this swimmer with the active loop pitching tail, what we see is that we see 2 ring vortices shed in the wake over one oscillation cycle. We don't see that in the reference case in the active loop pitching tail. But we do see one thing, which is the vortex that is that takes the vortex that has been created at the leading edge of the caudal fin stays attached to the surface and it does not shed. So this is considered to be contributing towards the production of thrust, and which is similar to what we see in the passive loop pitching tail as well. But here in the wake, we don't see a much more prominent vortical activity. So that is the reason we see better performance in the passive loop pitching tail with the displacement in same configuration to the active loop pitching tail. And here we can look at the vortex in much more close-up view, and this creates an inward jet-like effect in the streamless direction. For the vortex dynamics in the case of the inferior performing case, as we saw earlier, we do see much more larger vortex structures shedding in the wake. When we look closely, majority of these vortex that we see, they are tip vortices that creates much jet propulsion and the momentum of the velocity in the lateral direction rather than the streamwise direction. And we can see that from their orientation. And that's majorly contributing towards the pressure drag. And the second aspect is, if you look closely from the dorsal view, the leading edge vortex basically gets detached into components, and that detachment early on is considered to be producing drag as well. So from here, we can see the cycle average streamwise velocity for all 3 cases and understand how it's actually showing us how the whole cycle contributes towards either thrust or much more larger momentum in the wake. Here, in the active loop pitching tail and the best performing case and the inferior case, we can see there is a jet inclination angle we have used to demonstrate how narrow this jet effect is in the wake. In the active loop pitching tail, it spreads at 42 degrees, which is much more narrow in the case of best performing case, which is at 31 degrees, but it's very wide in the case of inferior performance. It goes up to 54 degrees. Now, in the case of best inferior performing case, we do see much more region where the velocity velocity is higher. And when we look at the minimum average velocity, that reflects exactly on the minimum velocity as well. We see alongside maximum velocity, there is a region with a wide spread of the minimum average velocity as well. So basically for the inferior performance of this case, it shows much more destruction of the vortex structures that does not contribute towards thrust. Whereas in the best performing case, the average minimum value is very narrow and it does not spread as much in the lateral direction, meaning it contributes heavily towards thrust. So from these analysis, we can make 3 key conclusions for 2-dimensional analysis and 3 for 3D, referring back to what we claimed in terms of our objectives. The active pitching tail does produce larger thrust than the passive pitching tail for 2D study. Although at 2D, we do see that we have better power ratio, going towards better performance at Reynolds number 500. And when we compare the kinematics, what we can see from the overall picture is that the smaller swimmer would perform better compared to a bigger swimmer, which reflects from the Reynolds number that we have chosen from 500 and 5,000. But when we look at the other side of the spectrum, which is in 3D, when we use the nonlinear stiffness, we can use the nonlinearity to amplify the pitching amplitude, and that does help us yield better performance in terms of its thrust reduction. And the consideration that we have made and the criteria is that it follows a very close trajectory to that of a Carangiform swimming mode. If it does not, then you will see distortion in the wake as we saw, and that will be contributing towards lower thrust and higher drag. And this study helped me have one of my journal paper under review in biomimetics, and the other paper is under preparation, hoping for submission soon in future. This work has an importance in terms of its future as well, which is that the passive pitching of the tail now can be also understood and analyzed in terms of its applications in a schooling configuration, because a lot of fishes, they do tend to move in schools. Further on, we can also use the flapping of the tail as a fully passive joint instead of having the heaving control in an active fashion. And the last stage of this study could be the model of this entire caudal fin with as a flexible body, mimicking exactly the kinematics of the swimmer, of Carangiform swimmer primarily in this case. I would like to acknowledge Digital Research Alliance and Lakehead University, also answered for the funding and helping me run my simulations on the supercomputers and clusters. And I would also like to thank everyone and Thesis committee member and my supervisors for taking the time out of.